Let us calculate the ripple factor of a capacitor filter. This is the output of a full wave rectifier where we get the output for both the half cycles of the input, and the waveform which is shown by the dotted lines represents the output of a capacitor filter, which is represented by A, B, C, D, E, etc. Here from peak to peak, the time period of the output of the full wave rectifier is T by 2. So this is half of the time period from A to C. So we represent it by T by 2. So from this point A to point B, the capacitor is in discharging state, and from B to C it will be charging. So let us say the time for which the capacitor is discharging is represented by small t, and if dq is the charge that is lost during the time t, then this charge dq I can write it as current into time, that is q is equal to I into t. So I write it as IDC into t, that is the charge lost during the time t or the charge discharged during the time t is given by IDC into t. Now the peak to peak voltage, as it is a triangular waveform, for that the peak to peak voltage I can write it as, using the relation V is equal to Q by C, I write it as V is equal to dQ by C. Substitute dQ from this equation 1, we get IDC into T by C. Now from the figure I can write this T, small t, approximately equal to T by 2. So therefore I will get here IDC into capital T by 2C, and the time period T can be written as 1 by frequency. So therefore I will get this equation for peak to peak as IDC into T is 1 by F. So therefore I can write it as IDC by 2FC, and the current IDC I can write it as VDC by RL. So this equation I can write it as VDC by 2FC into RL, where RL is the load resistance. Now the RMS value of peak to peak current can be written as, because it is a triangular waveform, the RMS value is given by 1 by 2 root 3 times of peak to peak value. So therefore by multiplying this with 1 by 2 root 3, we get VDC by, multiply with 2 root 3, you will get 1 by, this is 4 root 3 into FCRL. Let us consider this as equation 2. Now the ripple factor, we know that it is given by the RMS value of AC components VRMS by VDC. So if I substitute this VRMS value in this equation, I get VDC by 4 root 3 FCRL multiplied by, here we have 1 by VDC, so we write it as it is 1 by VDC. So this VDC will get cancelled. So you will get the ripple factor for capacitor filter as 1 by 4 root 3 FCRL. So the ripple factor of a capacitor filter is inversely proportional to the capacitance of the capacitor, and it is also inversely proportional to the value of the load resistor which we connect. So therefore for having a capacitor filter to be more efficient, we have to connect the capacitance as well as the load resistance of lower values, and also it will work efficiently if the incoming frequency values are more.